All right, hello and welcome to Math 3322. I am Dr. Heath. I am here to walk you through section 7.1 of our course. So chapter 7 is all about decimals, percents, and real numbers. So that's what we're going to be talking about. And this PowerPoint is posted without the video on Canvas. So section 7.1 is talking about terminating decimals. So what you should be able to do is and understand is decimal notation, connections between fractions and decimals, using a lot of different various models and strategies, why terminating decimals occur and how to tell if a decimal will terminate or not, and the ordering of terminating decimals. So it's just a big blanket forewarning. This section, it's going to be very tempting to just put everything into your calculator. Now, my math lab probably won't know the difference between if you do it with the calculator or with your by hand, but I want to encourage you to try to use some of these different strategies first before you go to using your calculator to just find the answer, because that's going to benefit you in the long run and for helping explain this kind of stuff to children in the future. So just a little history. The word decimal comes from the Latin decim, meaning 10, and the number system we use has its base number base 10. Now, if you ever do any computer programming or anything, you might know like binary, and that's base 2. We have other number systems we can work in different bases, but actually we use base 10, unsurprisingly, because most of us have 10 fingers and it's easy to count that way. So that's how we came up with a base 10 number system. So we can use different representations to highlight decimals and understand them better. So just to remind you, when we have a power, right, we can write, say, a to the n power, where n is greater than 0, then this means a times a. So when n is greater than 0, a to the n equals a times a times a times dot 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 times a n times. Okay, so 10 squared is 10 times 10, or 100. Now, to be clear, we also can use powers where n is less than 0. So n less than 0, a to the n would be 1 over a times a times a dot 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 times a. So if we have 10 to the negative 2, that's equal to 1 over 10 squared, or 1 over 100. So negative powers put us in the denominator. All right, so if we're trying to take this number 12.61843, which we'll learn how to say in just a second, but we can break this down by each place value. So we know that right here, this this 1 tells us that there's 110 in this number. So I can write that as 1 times 10. So this is from the 1 in that 12. Then we also have 2 1s. So again, that's where we get this 2 times 1. Now, things get a little more complicated when we start to go on the decimal side of things. So this first place value, where the 6 is called the tenths. So we have 6 tenths. So that's 6 times 10 to the -1, or 6 times 1/10, 6 1/10ths, which is where we get this 6 over 10 to the 1. And then we keep going, right? So the 1 here shows us our 100ths place. So that's going to be 1 100ths, which is the same thing as 1 times 10 squared, which is where we get this 1 over 10 squared. And then we have thousandths, which is when we have 1 over 1,000. So here we have 8 times 1 over 1,000, which is the same thing as 8 times 1 over 10 cubed. And you'll notice it's cubed, and we're in the third decimal place over. So that's where we get 8 over 10 cubed. Then we have 10 thousandths, which is 1 over 10,000, which is the same thing as 1 over 10 to the 4th power. And that's where we get 4 over 10 to the 4th. And then finally, we have our 100 thousandths, which is the same thing as 1 over 100,000, or 1 over 10 to the 5th power, which is where we get our 3 10 to the 5th power. So we have 3 of those. Okay, so this is one way we can represent decimal values. We actually read this number 12, and then our decimal point gives us the and 61,843 hundred thousandths. So since we have 5 decimal places, this is telling us this is how many hundred thousandths we have. We have 61,843 hundred thousandths. We could also read this number as 12 and 6/10, 1/100th, 8 thousandths, 4 10 thousandths, 3 100 thousandths. All right, so every reminder, we have each place value has a name that is based on its power of 10. So again, we had hundreds, tens, ones. The decimal gives us the word and, tenths, hundredths, then thousandths, 10 thousandths, hundred thousandths, and the next would be millionths. All right, so base 10 blocks are actually going to be pretty helpful in allowing us to represent numbers, including decimal numbers. So base 10 blocks, if you don't remember from when you were a kid or you never used them, we have one little tiny block, and usually in elementary school, we would use that to represent 1. And then the next size block up is our 10 block, which has 10 of these 1 blocks inside of them. Then we have a 100 block because we have 10 10 blocks. So we could think of it as 10 of these bars. Or we could think of it as 100 of the little tiny blocks. And then finally, we have a 1,000 block, which is 10 of these 100 blocks lined up together, right? So these are going to be able to help us represent numbers, including decimal numbers. Now we just have to get a little bit creative with how we represent decimal numbers. But we can ask ourselves, how could we represent 123 using base 10 blocks? So remembering that we have all of these different types of blocks at our disposal, we usually want to think about what's the smallest value I'm going to need to represent here. So I'm going to need to represent a 3, a 1, because my smallest place value I need to represent is the 1's place value. So we could say, let's let one of these blocks be our 1's place value. So I'm going to just draw it as a square because I can't draw three-dimensional bars. So I know that if I let a little block be 1, then a bar with 10 of these that will be representing our 10's place. And then the big block will represent our 100's. So to represent 123, I can have one big block. So that's 100. Then I would need 2 10's and 3 1's. And this is one way I could represent 123 using base 10 blocks. And I've got a nice visual for you here. So it's always important to let the person you're communicating with know what a block is supposed to mean, because we could also use these blocks to represent different numbers. So if we think about decimals, we need to ask ourselves, how might we represent 5.4 using base 10 blocks? So if we go back to the key and the system we used in the previous example, the small block equaling 1 is going to create problems for us when we try to represent 5.4, because we could say, okay, I need 5 1's because I have 5 1's in my 1's place. But then I run into a problem when I try to represent 0.4, because I don't actually have a smaller block than that 1's block. So if we start from the beginning by asking ourselves, what's the smallest place value I'm going to need to represent, and we let that little tiny block be that place value, then we'll be in a lot better shape. So I need to let the small block represent our 10ths, or 1/10, which is the same thing as 0.1. So now when I go to think about what a bar and a block will be representing, here a bar is 10/10 because I have 10 small blocks, which is equal to 1 1. So this is 1 now represented in this system. And when I take my big block, this is 10 1's, or 1/10. So I'm not going to need to use the big square here because I don't have any 10's in 5.4, but I need 5 1's. So if I go to represent this number here, I have 5 1's. And I'll need 4 10ths. So now this block represents 5 and 4 tenths. We could alternatively just have, instead of using all of these bars, used 10 blocks for every bar. And then I would have 50 tenths and 4 more tenths, or 54 tenths. So there are multiple ways we can represent this number using our base 10 blocks. In particular here, it's important that we have our little key representing what a small block is used to represent, because otherwise someone might look at this picture here on the right and say, oh, that's 54. But we're trying to represent 5.4, so we want to be clear that a small block is going to represent tenths. And here's just that explanation written out. Okay, so now we go a little deeper. How could we represent 2.235 or 2 and 235 thousandths? Right. So we have thousandths place as the smallest value we want to represent. So I'm going to need to let a small block represent the thousandths, which is 1/1000, or 1/10 cubed, or 0.001. So my small block is going to be representing thousandths. So that means that when I go to think about the bar, this is 10 thousandths because I have 10 of those small blocks. So 10 thousandths is the same as 1/10/1000, which is 1/100th. Or that second decimal place. Then our big block, our big square, excuse me, is going to be 10 hundredths, which makes 1/10. Now we also need to represent ones here because I have 2 ones in my number I'm trying to represent. So this is going to be represented by that big cube block that I had before in the picture on the previous slide, and I can go back and show you that. This block here on the left, that's going to be representing our ones, because this is 10 tenths, because I have 10 of these. I should have 10 of those flat large blocks. So this is 10 tenths, or 1. So when I go to represent this number and I have this key, I'm going to be having, see if I can draw it down here at the bottom. I need 2 ones, so I'm going to have 2 big cubes. That's my 2 ones. Then I need 2 tenths from this tenths value here. So that's 2 flat large blocks. 3 1/100ths. And 5 thousandths. So this should be how we can represent this value. And I have a much nicer picture for you here. Okay, So we also might want to take fractions and represent them as decimals. And we can do that in a lot of different ways. And this is, I think, where you're going to become tempted to think about using your calculator, but I'm going to try to walk you through some other ways we can think about this. So if we have 25 tenths, then that means I have 20 is 2 tens and 5 ones. So I can rewrite that number in our base 10 format here. And then I can split up my fraction. So I have 2 tens over 10 plus 5 over 10. And these two tens will cancel out because I have 10 divided by 10 is 1. So I have 2 plus 5 over 10. So that tells me that this is 2 and 5 tenths. Okay, we can do the same thing here with 56. So 56 is just 5 tens plus 6 ones over 100. And I can split this up. I've got 5 tens over 100 plus 6 over 100. And 100 is the same as 10 times 10. So I can take one of these tens and cancel it. So I'm left with 5 tenths and 6 100ths, which is 0.56. Let me clear this work, and then an easier way to think about this is I've got 56 out of 100, and so 100 is where our decimal starts. So I did it the hard way, but we can just automatically know that we have 0.56. And a lot of people like to think about this as a percentage as well, 56%, because cent is 100, and so 56 out of 100 is the same thing as 56% or 0.56. And then lastly, we have 205 out of 10,000. So 205 out of 10,000 is going to be 205 10,000ths. So we can think about this as remembering that our decimals go, so that's tenths, hundredths, thousandths, and 10,000ths. And I have 205 10,000ths. So I have 205 in this 10,000ths place. So I can write this decimal number as 0.0205. Okay, that's here. All right, and so now we can also think about how we can write different decimal values, different fractions as decimal values when we don't necessarily have a power of 10 in the base. The way we can do this is by making what we have in the denominator a power of 10. So remember that 10 is 2 times 5, right? So 100, or 10 squared, is 2 times 5 squared, and that's 2 squared times 5 squared. And we can do this with any power of 10. So 10 to the n power is going to be 2 to the n times 5 to the n. So here we have 2 to the 6th power in the denominator of this fraction. So what I can do is multiply on the top and bottom of this fraction by 5 to the 6th power. And I can do that because when I multiply on the numerator and denominator by the same number, I'm really just multiplying by 1. And when we multiply by 1, we get the same thing. So now I have 7 times 5 to the 6th over 2 to the 6th times 5 to the 6th, which is 10 to the 6th power. And then I know 10 to the 6th power is 10 with 6 zeros, or 1 with 6 zeros, excuse me. So that's 1 million. So I have 7 times 5 to the 6th over 1 million. And we can use our calculators to multiply out here and get 109 375, excuse me. So over 10 to the 6th, which is millionths, which tells me that I'm going to be at the 6th decimal spot also. Another simpler, excuse me, never mind what I was going to say. Now on the bottom example B, I have 3 powers of 2 and 4 powers of 5. So to make this in tenths, I can multiply both the numerator and the denominator by 1 more power of 2. So I'm going to multiply by 2, which will allow me to have 2 over 2 to the 4th times 5 to the 4th, which is 2 over 10 to the 4th, which is our 4th decimal spot, or the 1000th spot, because this is 2 over 1000, 10,000, excuse me. Here's that worked out for you. Okay, and now finally we have some more examples where we don't necessarily have it already broken into powers when we start. So we can factor our denominators here. So if I have 1 over 125, 125 is 5 cubed. And I can do the same thing I just did on the other page and multiply by 2 cubed on the top and bottom of our fraction to see and get a power of 10 in the denominator. So I have 2 cubed over 10 cubed. 2 cubed is 8 over 10 cubed, which gives me 0.008. Here's that typed out. And then 7 over 250, we need to factor 250. So 7 over 250, 250 is the same thing as 25 times 10. And 25 is 5 times 5. And 10 is 5 times 2. So I have 3 5s and 1 2. So this is 5 cubed times 3, or excuse me, times 2. And to get that into a power of 10, I can multiply the numerator and denominator by 2 squared. Because this will become 2 cubed. So now I have 5 cubed times 2 cubed on the denominator, and 7 times 2 squared over 10 cubed. This is 7 times 4 over 10 cubed, which is 28 times over 10 cubed. So 10 cubed tells me I'm in my 3rd decimal spot, 28 of those. So 2 hundredths, 8 thousandths, or 28 thousandths. All right, so all of the decimals that we've been working with so far have been terminating decimals, and these are decimals that we can write with a finite number of places to the right of the decimal point, and these are terminating. A rational number in its simplest form can be written as a terminating decimal if and only if the prime factorization of the denominator contains no primes other than 2 or 5. So in all of these examples we saw previously, these denominators had only factors of 2 or 5 in that denominator, nothing else. And just a reminder, a rational number is a number that we can write a over b, with a and b being both integers, and b is not 0. So pi is an example of a not a rational number, but 1 over 9 or 1 over 5 or 2 over 7, those are all rational numbers. So we can practice a little bit to see which of these is going to terminate and which is not. So we look at the denominators to do this. So if I look at 7/16, is this going to terminate or not? And remember that rule is that they terminate if the factors in the denominator are only 2 and 5. 16, however, though, is 4 times 4, which is 2, 2, 2, 2. So this is 2 to the 4th power. So this should terminate because we have 2 to the 4th power. So this is in the terminating side, 7/16, because 16 is 2 to the 4th power. All right. So if we look at the next example, 84. So if we try to factor 84, 84 is 2 times 42. 42 is 2 times 21. 21 is 3 times 7. So 84 is 2 squared times 3 times 7. So this has factors that are not 2 and 5. They have 3 and 7 also as factors. So this is going to go in the no category. So 9/84 because 18. Oh, excuse me. Because 84 is 2 squared times 3 times 7. All right. Next on the list is 26. 26 is 2 times 13. 13 is prime. So we also have a factor of 26 that's not 2 or 5. 26 is 2 times 13. Okay, 160. 160 is the same thing as 10 times 16. 10 is 2 times 5. 16 is 4 times 4. And 4 is 2 on either side. So I have 1, 2, 3, 4, 5 twos and 1, 5. So this will go in my yes column because 160 is 2 to the 5th power times 5. All right, 40. I'm trying to run out of space. 40, when we factor it, is 4 times 10. 4 is 2 times 2. 10 is 2 times 5. So 3 2s and 1 5. This is going in the yes because 19/40. 40 is 2 cubed times 5. And then lastly, 18. 18 is 3 times 6. 6 is 2 times 3. I'm running out of space here. There we go. So this is no, because we have a factor of 3. So this is 11 out of 18. It is not because 18 is 2 times 3 squared. All right, so you can pause this and look over it. And then I also have it typed out here for you. Okay, so a terminating decimal is easily located on the number line because we can represent it as a rational number where b is not 0 and b is a power of 10. So here we know if we think about 0.56 or 56 hundredths, we can write that as 56 over 100. And that's going to go on our number line between 50 over 100 and 60 over 100, which is the same thing as 5/10 and 6/10. So we can place these on the number line. We can also compare terminating decimals to see which is going to be larger. The easiest way to do this is to line up the numbers by place value and then think about what number is going to be larger here. So they have the same number of tenths, the same number of hundredths, but then one of these values has more thousandths than the other. So if we start at the left, again, we can see that the top number is going to have 6 thousandths, whereas the bottom number only has 5 thousandths. So that number is greater. And that's the end. So I hope this video has been helpful for you. And as always, give me an email or post on our course questions discussion board if you have any questions. You should now be prepared to do your Unit 7.1 homework on My Lab Math. So thank you and have a good day.